Yes. Hi everyone. Good morning. Good morning to everyone. Yes. Do you have any questions in the last session, guys? Anybody have any doubts, any questions, anything to discuss? Right. Okay. So in the last session, we have started with the introduction to decision tree, its interpretation, and building decision trees. We have seen several advantages of tree models over linear model, and we have seen some terminologies associated with decision tree, how it is it helps us interpretability. Then we have taken some examples. These are the steps, right? Greedy approach we have discussed. It's a overfitting model. To overcome overfitting, we have regularization and cross validation. That is not something which we are going to discuss now, as I told, because this comes under your improvement in the model performance. We are going to discuss this separately. Then we have seen bias variance, right? And we have taken an example. We have seen Occam's razor principle, right? And these are the advantages of simplicity and disadvantages of simplicity, right? I think uh, it is completed, right? This part is completed. Just let me have a check. Okay. All right. I think only last part which is remaining is your Mhm. uh, is it completed, guys? This part, your decision tree model building, was that completed? Decision tree model building, was that completed or not? Okay, this is something which we have done. Just let me check. Yeah, I think it's done, right? Okay. Okay. So let's start with the two parts. First is hyperparameters, which we are going to study in today's session. So what are the hyperparameters? You saw the decision tree is not performing well on your testing dataset, right? We are getting only 60% accuracy in the testing dataset, and we are getting 74% accuracy in your training dataset. So I can say model is not performing well, is not performing well on the test data. Yes or no? So this is because we built our model on a default parameters, right? We built our model on default parameter. What are the default parameters? We have not added any parameter over there while building a model, right? For an example, whenever I created the object, that is your decision tree, whenever I created an object that is decision tree, uh, I have only added max depth. That's all. I have not added anything. Yes or no? So if you go to official documentation of sklearn and decision tree, you can see there are n number of parameters that we can use to get or to increase the maximum accuracy, right? For an example, if I use criterion, I should add Gini or entropy or log loss. These are the permissible values. If I use splitter, I can add best, I can add random. Max depth, I can add any integer. So that is the limit. Minimum sample split, any integer or float values are accepted. Minimum sample leaf, any integer or float value is accepted. Minimum weight fraction is any float value. Maximum feature is any integer, float, or square root or log 2 value. So if you just scroll down, you can see n number of parameters, and there is no need rule that you should use all the parameters or you should use only specific parameter. There's no any rule as such. So you don't have to worry about that. You can use any parameter out there depending upon your wish, right? Now, each parameter has its explanation over here, and there's no any need to study every parameter out there, right? So you can explore this article where you can get to know what is random state. Anyway, we have discussed that. You can get to know what is maximum features, the number of features to consider when looking the best split. You can get to know minimum weight fraction leaf, that is minimum weighted fraction of the sum total of weights of all the input samples required to be at a leaf node, and samples have equal weight when samples weight is not provided. We have minimum sample leaf, that is minimum number of samples required to be at a leaf node. A split point at any depth will only be considered if it leaves at least minimum sample leaf, training samples in each of the left and right branches. This may have the effect of smoothing the model, especially in regression. So you can read this. It's not that important. So that's the reason I'm not taking this. So we built our model on default parameters. We have not added any parameter out there, right? Only max depth is added. And that's the reason we did not change any other hyperparameters. So we have one concept which is known as hyperparameter tuning, which can improve the performance of decision trees to a great extent. So in the upcoming session, we will go ahead and exploit this parameters to improve the model and give the better prediction results, right? Now, what are the hyperparameters? Hyperparameters are simply the parameters that we pass on to the learning algorithm to control the training of the model. And there are different choices that told. You can select any hyperparameter out there. That's not a problem. The choices are the choices that the algorithm designer makes to tune the behavior of the learning algorithm. The choice of hyperparameters, therefore, has a lot of bearing on the final model produced by the learning algorithm. So basically, anything that is passed on to the algorithm before it begins its training or learning process is a hyperparameter, right? So if I pass criterion, Gini entropy before training actually, which is over here, that is my hyperparameter. So max depth is my hyperparameter over here. I can add any hyperparameter, comma, I can add minimum sample split, right? Minimum sample split. I can paste it over here. The values are which are permissible are nothing but any integer value. So you can add any integer value, let's say 4, right? So these are known as hyperparameter. Ideally, before training the model, the values that you add are known as hyperparameters, right? So these are the parameters that the users provide, not something that the algorithm learns on its own during the training process. And here, one of the hyperparameters you input was max depth. So we'll just keep that only, max depth, which is essentially determines how many levels of nodes you will have from root to leaf, from root node to leaf node. How many level of nodes will you have from root to leaf? And this is something that the algorithm is capable of determining on its own and has to be provided by the user, right? It is something which is incapable of determining, which your model is incapable or algorithm is incapable of determining in its own. So that's the reason you have to specify that, right? Now, obviously, since the hyperparameters can take many values or any values, So it is essential for us to determine the optimal values where the model will perform the best, right? So it is our duty to find the best value, that is optimal values of the hyperparameters that we are passing, right? So I can, if I just pass max depth, I can pass it in a list as well. Suppose if I pass max depth, so that can be max underscore depth can be, it can be a list, and I can add any integer value, a list of that. It is totally my wish. And suppose if I pass this parameters, so ideally there should be only one max depth value which will result, which will give us the maximum accuracy, right? Suppose you, if you pass max depth equals to only six, then only you will get maximum accuracy out of this, right? Do you agree with this fact? There are, I mean, this is very common sense that if I pass max depth equals to 1, I'll get some accuracy. If I pass max depth equals to 2, I'll get some accuracy. Similarly, 3, 4, 45, 6, 7, 8, I'll get some accuracy for this values, right? And out of these values, out of this accuracy, there will be one maximum accuracy. Yes or no? So if you select that, you'll be able to improve your accuracy. You'll be able to improve your model's performance. Yes or no, guys? Right? So that's the reason we do the hyperparameter tuning. So it's a very simple concept and which is very effective as well, which we should use to increase the accuracy of your model. Right? So I'll just highlight this because it's a separate topic. So we have to tune that. And this is known as tuning, like to find the best values out of the list of the hyperparameters. So the process, so the process um, of optimizing hyperparameters, excuse me, is called is called hyperparameter tuning, right? And you learn to do this in the next part, let's say after some time, after half an hour. So that's what we have, right? That's what we have for the hyperparameter tuning. Now we just have uh, started this point, that what are the advantages of tree model over linear models. So there was a topic, right, which you can see over here, tree models over linear models, right? So what we'll do is we'll just write down this heading, right? We'll just increase the font if it is necessary. I think we should do 20. Yeah. And that's what. Okay. So, so far you have learned about linear and logistic regression for classification regression problems, and they are able to make predictions using these models. You have learned to find or to make predictions using this model. So what is the need of tree models over here, right? Aren't your linear models enough for this purpose? Yeah. So there are certain cases where you cannot directly apply linear regression to solve a regression problems. Linear regression fits only one model to the entire dataset. However, you may want to divide the dataset into multiple subset. You may want to divide your data into multiple subsets, right? And apply decision tree, apply decision tree algorithm, right? In such cases to handle non-linearity. Now, I'll just draw one figure in order to explain this particular point that we have just discussed. Just a minute. Yeah. So suppose you have the same example that we can take is uh, the heart to predict whether the person has heart disease or not, right? So suppose uh, on y-axis you have cholesterol level. On x-axis you have age, right? And let's say you have different lines. This is segment one. This will be your segment two, and this will be your segment three. Let's take this, right? So we are dividing our data into three parts because the behavior of the data is like this, right? You cannot do anything. So it has non-linearity. It is not linear. It has non-linearity in the data set. So what you can do is if you apply linear regression model to this entire line over here from this to this, it will not help you out, right? So instead of that, you apply decision tree, you divide your data into three subset, right? And you apply decision tree where one leaf will be age less than 25, leaf two will be, let's say, be in between 25 to 60, right? And leaf three will be age is greater than 60, right? Leaf three will be age greater than 60. Yes or no? So if you have data like this, you can easily implement tree models over linear models. So this is benefit number one. Like suppose the behavior of the data is as such, as you can see in the figure, your decision tree model will only be the solution. Your linear model will not be the case over here. And you can make different predictions, 1, 2, and 3, and you can then just take an average of that, or you can do this thing, right? So that is one of the disadvantages of linear regression model. Apart from that, you have uh, interpretability, which we already have discussed. It is interpretable, right? It's very self-explanatory. It does not require any explanation, self-explanatory, so that any common man will be able to find out how you have approached this problem, right? You just draw a decision tree like this, simple. And the example that we have taken to predict whether the person has heart disease or not, it's very simple and easy, right? Everyone can easily understand this thing, or this, let's take this, right? So there is no any fancy thing that we are doing. We are just solving our uh, problem by just using this, right? This is simple, and anyone can understand how we have approached this problem. So it's interpretable. Second is, it is versatile. Decision trees is versatile in nature. It does not assume anything specific about the nature of the attributes in a data set. It can seamlessly handle all kinds of data, such as all kinds of data, such as numeric, categorical, strings, and Boolean, etc. Right? And a decision tree is a scale invariant. What do you mean by that? It does not have any effect of different scales. You do not need to use normalization, standardization. So it does not require normalization, as it only has to compare the values within an attribute, right? So it can handle multicollinearity very well. It does not require normalization, as it only has to compare the values within an attribute. The next point is it handles multicollinearity. What is multicollinearity, guys? What do you mean by multicollinearity? Come on, I told you to discuss, right? You have to discuss. You have to turn your mic on and discuss something. So what is multicollinearity? We have seen this, right?
When the independent variables are highly correlated to each other, then multicollinearity is possible.
Okay. Yes. Very good. And how do you remove that? How do you remove multicollinearity?
We can remove the data that is highly correlated.
Then using VIF. Yes, very good, Murali. We use VIF, right? All right. So if VIF is greater than 5, we say that multicollinearity exists and we have to remove the multicollinearity by using different approaches that we have not discussed till now, right? Now, dysentery often gives us an idea of the relative importance of the explanatory attributes. What do you mean by explanatory attributes? Simply independent variables. Independent variables. Independent variables means, suppose you have, uh, you are doing splitting based on the age, first of all, and you're getting some accuracy, right? Something like that. Suppose you are doing splitting based on the cholesterol level of the patient, and you are getting some accuracy. So suppose if you do splitting based on the cholesterol level, you will get more homogeneous split. We'll come to this point, homogeneous. The reason being why I have just now introduced this concept of homogeneity, because that is something which we are going to discuss in our entire session today, right? It's going to be very interesting. So suppose I have 10 data points, right? I have 10 data points. And if I do splitting based on the ages, age is less than 60 or something like that, I am getting, let's say, 8 and 2, right? Right. I'm getting 8 and 2. If I do splitting based on the cholesterol level, I am getting split like, let's say, let's take hypothetical scenario 5, 5. So which one is more homogeneous? What do you think? Which one is good or which one is bad for our model? The splitting should be as pure as possible, right? It should be pure, it should be homogeneous, non-homogeneous, not homogeneous basically. It should be non-homogeneous. We'll come to this point, meaning that you should be able to easily take up the decision. For an example, this is 8, if this is 2, I can get confidence of splitting over here, like 8 should be the correct answer and 2 should be the, or basically left hand side we have 8, right hand side we have 2. So there is clear cut segregation of the two data points or two classes, right? But if it is 5, 5, isn't it an ambiguous part? Let's say you got 5 votes for, let's say, BGP, right? And you got same vote for Congress. So it's a non-homogeneous, right? Sorry, uh, it is not pure, right? Splitting is not pure. So there is ambiguity. So our entire purpose of decision tree is to increase this purity, and we have several ways to do that. We'll come to this point after some time. So the decision tree gives an idea about the relative importance of the explanatory variable. Like if the splitting is pure based on some parameters, let's say if I go with the age and I'm getting pure splitting, so I can get an importance of that independent variable, that yes, age is having high importance rather than cholesterol, right? Because cholesterol is not giving me the pure splitting, right? So by just understanding the magnitude of splitting, we get the relative importance of the explanatory variable. Then they are highly efficient and fast algorithm, and they can identify the complex relationships and work well in certain cases where you cannot fit a single linear relationship between the target and feature variables. So this is where regression with decision trees comes into the picture, right? So in regression problems, decision tree splits the data into multiple subset, and the difference between decision tree classification and the tree regression is, in regression, each leaf represents the average of all the values of the predictions, as opposed to the class label in the classification, as we already have discussed this. So basically, in classification problem, we take majority of the votes, right? Classification is, we take majority of the votes. Suppose if you are working on classification problem, let's say disease and no disease, right? Disease and no disease. So suppose for disease you have 34 outcome, and for no disease you have 12, right? So based on the majority of the vote, we will go for prediction as disease. The person has disease, like that. Prediction is disease. And in classification, in regression, what do you do is you take average value of the node, right? So taking the average value in case of your decision tree, sorry, regression, average value, right? And this average is calculated using the formula which you can see. For example, you are predicting sales of your company, which will have based on the various factors such as marketing, number of products, right? And you want to predict the sales of the company, sales of the company. So if you have five data points, let's say 1 crore, 1.3 CR, 0.97 CR, sale of your organization, 0.97 CR, 1.22 CR, 0.79 CR, right? And now you will just take the average of these five values, which comes out to be average, which comes out to be 1.05, and that becomes your final prediction instead of uh, taking this everything over there, right? So you take average, and decision tree classification is what you will most commonly work on. However, remember that if you get a data set where you want to perform regression, decision tree regression is also a good idea, right? That's what we have. Now we will discuss our today's agenda, which is the algorithms for decision tree construction. So for that, what I'll do is I'll just create a new sheet and let us start discussing that. So today is 4th Jan, right? 4th Jan. All right. Okay. Now, in the previous session, let me just add the entire title of this first. Decision tree construction or algorithm for decision tree construction. And let me tell you, this is going to be the uh, highly important topic in your decision tree session, right? So this is your important part, which is very important, which is highly crucial as far as the interviews are concerned, right? So let us start with this. In the previous session, you learned about the underlying concepts of decision trees and their interpretation. You also learned how to construct a decision tree. You learned about the advantages of decision trees and also understood how they help in solving regression problems that cannot be handled by linear regression. In this session, you will learn about the methods for decision tree constructions. So in this session, you are going to learn splitting, splitting and homogeneity. I just have given a trailer to this point, right? Homogeneity. Now you have to see the entire thing. Then we have impurity. We have impurity measures. We have best split, and we have regression trees, right? So I'll just take this and I'll highlight this. So this is our agenda for this entire session. So without wasting time, we'll just discuss first point, that is splitting and homogeneity, right? So let me add heading. Right? Okay. So recall the scenario from the session one where you were a doctor asking a series of questions to determine whether a person has heart disease or not. Based on your past experience with other patients, the answers to these questions would finally lead to a predictions depicting whether the person has heart disease or not. Now, if you are a doctor, you would know which questions to ask first, right? When the person might at risk of heart disease, the doctor would probably first ask or measure the cholesterol of the person, right? Let's say you're asking cholesterol of the person, right? If let's say it is higher than 300, the doctor can be pretty sure that person is at risk, right? Then he may ask some more questions to confirm his predictions even further. So he may ask some more questions to this. Okay. Now, suppose instead of asking or measuring the cholesterol, the doctor first asks the age of the person. If the person says, say 25, the doctor may not be completely sure whether the person has heart disease or not, right? So, doctor may not be completely sure whether the person has heart disease or not. So basically, he or she would need to ask further questions. And from both these scenarios, it is easy to infer that to predict the target variable, in this case, heart disease, in this case, heart disease, there are obviously some questions or attributes that are more important for its predictions than other. Yes or no? So there are some attributes, we can call it as attributes, that are more important for its prediction than others. For an example, cholesterol. So in our case, you saw the cholesterol level is a more significant attribute than age in the predictions of heart disease. Why is that? It is because for doctor it might be evident from the past records that the people with will that the people will higher cholesterol levels have a higher chance of having heart disease. Say in his or her experience, that doctor has seen that out of every 100 patients, every 100 patients having who have cholesterol higher than 300, higher than 300, 90 had heart disease. 90 had heart disease out of 100, right? And 10 does not have. 10 did not know heart disease, right? On the other hand, out of 100 patients that the doctor has consulted over the age of 54, let's take age criteria now. 100, same, we are taking same count, that is 100 patients, but this time age is greater than 54. 50 of them had heart disease and 50 of them has no heart disease, right? Now it is evident that cholesterol would be better to determine heart disease than age, since 90% of the patients having cholesterol greater than 300 were diagnosed with heart disease. Yes or no? So that is what your homogeneity concept is. So suppose these are the 100 patients based on you're doing splitting based on the cholesterol. 90 has heart disease, 10 has no heart disease. On the other hand, if I take age, if I just split, it will be 50-50. So which one is correct? Which one is more desirable? This one, 90-10. Because from this, you get a clear idea. There's no any confusion or ambiguity in your prediction. So we should go further with that. Yes or no? Do you have any questions till now? Anybody have any doubts, any questions till now? So I can clearly see that one of the classes, disease, is significantly dominant over other after splitting on the basis of cholesterol greater than 300. And this dominance is helping the doctor to make more confident predictions, unlike age, which gives a 50-50 split of both classes, leaving us in a dilemma again. So we basically arrive at these questions given many attributes. How do you decide which rules obtain from the attributes to choose in order to split the data set? In order to split the data set. From a single feature, you can get many rules. You may use any of this to make the split. Do you randomly select this and split the data set? Or should there be a selection criteria for choosing the split? For an example, cholesterol is greater than 300 or age is greater than 54. Do you randomly select this split? Or there should be a criterion. So what are you trying to achieve with the split? That is your second question. So you might be having a list of questions in your mind that do you randomly select this and split the data set? Second question could be, should there be selection criterion for choosing one over other? And what are you trying to achieve with the split? What are you trying to achieve with the split? All these questions will be covered in the following session, and you will learn about the various algorithms and criterion that are involved in construction of decision tree, right? Okay. So let us understand this. Yeah. So the concept of splitting and homogeneity, that is what is a split trying to achieve? What is a split trying to achieve? So first is homogeneous or pure subsets, right? Homogeneous means it should be having same after splitting, you should be at a position where it should be homogeneous, right? Just give me a minute, guys. Okay, so what we are talking is what our split is trying to achieve. Our split is trying to achieve the homogeneity. It should be like this 10 0. That is the ideal case. Or even though if it is not 10 0, it will be 9 1. That is also accepted. But it should not be like this 5 5, or it should not be like this 6 4. That is purely non-homogeneous splitting, right? So what do you mean by homogeneity? Is it should be uh 10 0 9 1, something like that, right? So the more the homogeneity, lesser will be the variation, and hence better will be the split. Better will be the split, right? More the homogeneity, lesser will be the variation, and hence better will be the split. So as I have discussed, suppose if you are doing splitting, and if it is like this 50 50, so it is completely non-homogeneous, right? Completely non-homogeneous. That is non-homogeneous. Non-homogeneous. And on the other hand, if you are doing splitting, which is 100 0, this is completely homogeneous. Completely homogeneous, right? So that is your definition of homogeneity, right? Now, if this is, if is it clear, guys? What do you mean by homogeneity? Do you have any questions in this concept of splitting and homogeneity till this point? Anybody have any questions? So as I have discussed, it is completely ideal case, right? 100 0 is completely ideal case. If the partition contains data points with identical labels, then you can classify the entire partition as that particular label. However, this is oversimplified example. In real world dataset, you will almost never completely will be having in real world datasets. You will almost never have completely homogeneous data sets or even nodes after splitting. After splitting the data. Hence, it is important that you try to split the nodes such that the resulting nodes are as homogeneous as possible. Hence, it is important that you try to split the nodes such that the resulting nodes are as homogeneous as possible. And one important thing to remember is that homogeneity here is always referred to response variable. That is target variables homogeneity. Homogeneity is always referred to response or your target variables homogeneity, right? For example, let's suppose we consider the same heart disease example in which you wanted to classify whether a person has heart disease or not. If one of the nodes is labeled blood pressure, you try to split it with a rule such that all the data points that pass the rule have one label, and those do not pass the rule have different label. Thus, you need to ensure that response variables homogeneity in the resultant splits is as high as possible. Suppose a split that results in a homogeneous subset is much more desirable than the one that results in 50-50 distributions. In a completely homogeneous set, all the data points belong to one particular label. Hence, you must try to generate partitions that result in such sets. For classification purpose, a dataset is completely homogeneous if it contains only a single class label. For regression purpose, a dataset is completely homogeneous if its variance is as small as possible, right? So classification has homogeneity concept as a dataset or yeah, a dataset is completely homogeneous if it contains only a single class label. But for regression, we have some other criterion, that is variance, right? A dataset is completely homogeneous if its variance is as small as possible. You'll understand regression trees better in upcoming segments. And anyway, I have discussed in my, I mean, as I discussed, 90% of the times you guys will be dealing with the decision tree classification problems only in the industry itself. Hardly or rarely you'll find some regression problems over which you can fit the decision trees, right? So in real world scenario or in industry as well, classification is something which we are going to use more predominantly while working as with the decision tree, right? Now let's take a look at the illustration given below to further understand homogeneity. Consider a dataset D with homogeneity H and defined threshold value. With homogeneity exceeds the threshold value, you need to stop splitting the node and assign the predictions to it. As this node does not need even further splitting, it becomes a leaf node, as you guys already have understood. We already have discussed what is leaf node. The node, it is a node which does not need further splitting. Yes or no? For an example, in this case as well, in the last session, we have discussed the concept of leaf node, leaf node over here, right? Leaf node. What is leaf node? This is your leaf node. The node from where further splitting is not possible. Yes or no? The node that cannot be further classified or cannot be further classified or split is called leaf node, right? Now, when you first of all you set the homogeneity threshold value in your data set. Suppose let's say you have a data set, right? You have a data set. Suppose 1, 2, and these are the other data points. 1, 2, 3, 4, 5. And let's take this, right? Now here, uh, suppose you keep threshold value of the homogeneity as 70%. The homogeneity of the node in the illustration given below is clearly above 70%, right? Homogeneity for this particular data set, which you can see in this figure, it is 86%. Like out of the 100% data, 86% are the homogeneous data, right? The homogeneity value in this case falls above threshold limit, which we have set above threshold limit. Hence, no splitting is required, and this node becomes a leaf node, right? This node becomes my leaf node. Uh, so that is uh, your question, like when to stop the splitting. When should we stop the splitting? Whenever the threshold value that you put while building a model is achieved, you do not need to split the data further, right? So split further for this case, you can say no, right? So what I'll do is I should take a screenshot of this and I should paste it over here itself so that it will be yes, and I can remove this diagram. Perfect, right? So that is what we have for this. Now keeping the same threshold value as 70%, you can see from the below illustration which I'm going to draw. Suppose uh, you have another data set which I'm drawing over here. One, two, three, four, five, six. Right? Further splitting is done. Further splitting is done. And one, two, three, four, five, six, seven. And we only have one and two. Right? Here also. One, two, and we have one, two, three, four, five, something like that. Right? So in this case, your homogeneity is H. Your homogeneity is H, right? And where H is less than threshold, where H is less than threshold, yes or no? Our threshold value is 70%, which we have said, but here it is 50%, right? We have uh 50% data which is of class red, 50% data which is of class black, right? So do we need to split further? Do we need to split further? Split further. Yes, because it's not a leaf node. What's your criteria of leaf node? Homogeneity should be greater than threshold. In this case, which is lesser than threshold, right? In this case, it is lesser than threshold. So that is a scenario number two, which I can uh, draw, which we will paste it over here, right? And I should remove this so that, yeah. Okay. So now keeping the same threshold, first in the first node itself, the homogeneity is exactly 50%. And the node that contains equal number of data points from both the classes, hence you cannot give a prediction on this node, and it does not meet the passing criterion which has been set. There is still some ambiguity existing in this node, this one. There's still some ambiguity present in this node, and there's no clear clarity on the label that can be assigned as the final predictions. This brings in need for further splitting, and we compare the values of homogeneity and threshold again to arrive at a decision. This is continued until the homogeneity value exceeds the threshold value. This is continued until the homogeneity value exceeds the threshold value. Until the homogeneity H is less than the threshold, you need to continue the splitting the node, right? And the process of splitting the nodes to be continued until homogeneity exceeds the threshold value and the majority points in the dataset are of same class. And that is what we have for the entire decision tree algorithm steps, right? And this is an abstract example to give you an intuition on homogeneity and splitting. You'll get better clarity for about this in the next part. After some time, we are going to discuss this. When you will learn to quantify and measure homogeneity to arrive at a predictions through a continuous splitting, right? So having understood the concept of splitting, we are going to discuss some concepts like measures like homogeneity, uh, measures to we will learn how to use specific methods to measure this homogeneity. So quantitatively we'll do that. This is qualitative analysis, and which is known as measure to uh, how do we count homogeneities? We have Gini index, we have Gini index, we have entropy, and we have classification error. Out of this, we are going to focus on only uh, Gini index, which is popularly used in the industry. But I'll just explain why. We'll just discuss these three concepts, and then we'll discuss why Gini index is important, right? And we still have one more thing, which is known as mean square error, which is used for regression purpose. So the error metrics, as we have discussed, evaluation metrics which we use for your regression is mean squared error and other forms of error, root mean square error. For classification, we used to use classification, report, confusion matrix, precision, recall, right? So this is for classification. This is for classification. All right. Now, how do you handle best split for different attributes in a decision tree using your decision tree algorithm? So there are various other techniques to like calculating percentiles and midpoints of the sorted values for handling continuous features in different algorithms. And this process is known as discretization, even though it is beyond our scope of this entire syllabus. But I'll just put a point where you can explore this further. Uh, if you are interested, you can go and explore this concept of discretization. So there are other various techniques like calculating percentiles and midpoints of the sorted values for handling continuous features in different algorithms, and that is known as discretization. So what is discretization? Anyway, this is beyond the scope of your course. You guys have to go further with your study. If you are interested to go for masters or research, if you want to do research in this domain, you can go and explore this discretization part, right? So although exact technicalities are out of the scope of this module, but curious students can read more about this uh, in the from the link that I'm going to share, right? So there's one research paper which you can find. Just give me a minute. I'll just share that thing with you. Discretization and enabling technique. Yeah, this is that particular thing. I think it's publicly available. Yeah. Yes. Makes sense. Okay. So you can go and explore this. So I'll just copy this link address and I'm going to paste it over here for your discretization, right? All right. So let's take a break for 10 to 15 minutes. 10 minutes or 12 minutes will take. And then here comes some mathematical discussion about the measures of impurity. And anyway, it's very interesting, but still little challenging for those guys who feel mathematics as some challenging part, right? So we are going to deal with the formulas. Anyway, the formulas and the calculation is not required for you, but it can be asked in the interviews, like what are the different impurity measures, how you calculate the entropy, how you get an idea about your model performance, and basically the significance of these three terms. You can expect these questions in the interview, right? So let us discuss this freshly after the break. It's 10:11. Let's have a break till 10:24. Yeah. If you have any questions, you can paste it in the chat. We'll discuss this after the break. Okay. So now you have narrowed down the decision tree construction problem to this. You want to split the data set such that the homogeneity of the resultant partitions is maximum. But how do you measure this homogeneity, right? So various methods such as classification error, Gini index, and entropy are the can be used to quantify the homogeneity, and you'll learn about this each method in the upcoming session, right? So first we have classification error. So I'll just write down over here. First one as classification error, and which is nothing but E is equals to 1 minus maximum of pi, right? So my case one is we will consider different cases so that you'll understand uh, the classification error concept. Suppose there is one splitting as 0.20 and 0.8. So splitting is like this 80-20 splitting, right? So class 0 is 20, class 1 is 80, right? Class 0 is 20, class 1 is 80. Then probability of 0 class will become 20 divided by total, that is 20 plus 80. That becomes 20 divided by 100, right? We have P1, which becomes 80 divided by 20 plus 80, and which becomes 0.8, right? Which becomes 0.8. So that becomes your probability of class 1 and probability of class 2. What your classification error says is 1 minus probability of maximum, whatever maximum probability that you have over there. So out of this, what is your maximum probability? 0.8. So classification error is equals to 1 minus P max, and which becomes 1 minus 0.8, and which becomes 0.2, right? So your classification error in this case becomes 0.2, right? That becomes your first and simple classification error concept. Second is Gini impurity, right? Second measure that we have is Gini impurity. And what is that? Is nothing but it's a summation of I is equals to 1 to n probability of I into 1 minus probability of I. Right? That becomes a formula. So I'll just take this. Now I'm going to paste it over. Right? That is your uh, Gini impurity formula. Right? Now, in this case only, case 1, probability of 0 is 0.2, probability of 1 is 0.8. So the formula becomes is equals to, or probability of 0 into 1 minus probability of 0 plus probability of 1 plus probability of 1 into 1 minus probability of 1. And that becomes your formula. And which exactly becomes 0.2. That is your probability of 0 into 1 minus 0.2. 0.2 into 1 minus 0.2 into 1 minus 0.2 plus 0.8 into 1 minus 0.8. Okay. And what is happening is not available. Okay. Into should be there. That becomes 0.32, right? So your Gini impurity becomes this one. And you have third measure, which is your entropy, which is your entropy. And again, which has a formula which becomes summation of I is equals to 1 to k probability of I into log of probability of I, right? Now, if I just take a screenshot of this, if I paste it over here, and if I put this in a formula here, so my entropy becomes minus probability of 0 into log of probability of 0, log of probability of 0 minus probability of 1 into log of probability of 1, right? And it becomes is equals to minus 0.2 into log to the base 2, log of 0.2 plus plus, or we can write on minus because formula is minus. Probability of 1 is 0.8 into log of minus 0.8, which is there, right? So I think is okay. Let me do this separately like this. And we have 0.8 into log of minus 0.8 is this should be equals to numeric error because we are taking minus cheese. And so basically, if you do this calculation, your Excel is or your Google Sheet is not doing this. You do it in by using calculator. It will be 0.72. Now you have entropy as equals to 0.72. You have Gini impurity is exactly equals to 0.32, and we have a classification error which is your 0.2. So now we have understood the formula and how do you calculate that. Now we'll see the significance. What is the importance of this classification error and Gini index and entropy, right? That is your case one. Let us take case number two to compare this. What was your case number one? 0.8 and 0.2. That is your 80-20, right? Split is homogeneous, quite homogeneous. But what if I have case like this where my class 0 is 0.5 and my class 1 is also 0.5, right? So my probability of 0 becomes 0.5, probability of 1 becomes 0.5. And what about classification error? 1 minus probability of maximum, which is equals to 1 minus 0.5, which is 0.5 only, which is 0.5 only, right? What about Gini impurity? You try to calculate that by using formula. Gini impurity. It is probability of 0 into 1 minus probability of 0, right? Plus probability of 1 into 1 minus probability of 1. And that becomes 0.5 into 0.5 plus 0.5 into 0.5. So becomes 0.5 only, right? It becomes 0.5 only. And what about entropy? What is your entropy? That is also becomes 0.5. So minus probability of 0 into log of probability of 0 minus probability of 1 into log of probability of 1. is equals to um, minus 0.5 into log of 0.5 plus or minus 0.5 into log of 0.5. So this becomes 0.5 log of minus 0.5. This should be, and it will give us the number error. This is also 0.5. Sorry, this becomes 1. So if the case is like this, 0.5 and 0.5, your entropy is 1, your Gini impurity is 0.5, and your classification error is 0.5. That is your case number 2, right? And what about case number 3, where where it will be opposite to case number 1? My probability of class 0 will be 0.8 and probability of class 1 will be 0.2. As you can see over here, right? Probability of 0 is 0.2, probability of 1 is 0.8. Here it is opposite. Probability of 0 is 0.8, probability of 1 is 0.2. So you have classification error as 0.2. Classification error. I'm directly writing it down now so that you don't need to calculate. Where is that? Yeah, here. So classification error becomes 0.32 or 0.2. You can calculate that. Gini impurity becomes 0.32 and entropy becomes 0.72, right? That becomes your class number 3, case number 3. Now, if you just take out the comparison, a diagram between impurity measures uh, entropy versus entropy scale versus Gini impurity versus misclassification error, right? If you just take this diagram, this is what I'm talking about. You'll get this over here. Yeah, this one. So, so the figure is this. This is your figure, right? This is your figure. And you can see color for, is it identical in this case? Yeah, here I think it's identical. Okay, let's take this only. Or entropy and this is also something which is good. This is what I'm talking about. Yeah. So if you just compare this all the uh, three concept, entropy versus entropy scaled versus Gini impurity versus misclassification error, you'll find that from the above example, you understood that which is the correct measure or which should be the ideal measure that you have. So your blue line is misclassification error, which starts from 0, maximum is 0.5, ends at 1. Your red is entropy scaled, which starts from 0 only. It is like this. Gini impurity is somewhat similar to entropy scaled, which is also starting from 0, maximum at 0.5, and this. And your entropy is 0, 1, and this. So ideally, your Gini impurity should be the correct measure or a good measure that we should go with. The It's a degree of randomly chosen data point being classified incorrectly. And the scaled version of entropy, which is read over here, we'll just write down that. Write down that. It's a entropy divided by 2. It's a illustration shown. You can also watch the video. It is also not important, but there's one video out for this one, over which uh, you can understand the entire concept of comparison between these three measures out there,
about
right?
40.
To just summarize this in a nutshell, from the above example, you understood how to calculate impurity measures and how do they change with different class distributions. You have impurity measures, you have classification error, you have Gini impurity, and you have entropy, right? Then you have case number 1, that is class 0 is 0.2, class 1 is 0.8. Classification error becomes your, it should be here, no. Classification error becomes 0.2. Here it was 0.32. Here it was 0.72. Case 2 was class 0 is 0.5. Class 1 is 0.5. Classification error becomes 0.5, 0.5, 1. And here it is your case number 3. That is also class 0, 80, class 1, 20. So 0.2, 0.32, 0.7, right? And if you just take this out, you can see for a completely non-homogeneous data with equal class distribution, that is this, the value of classification error and Gini impurity are same, 0.0.5, and entropy is 1. The scaled version of entropy is an illustration, is nothing but it is entropy divided by 2. Scaled version of entropy. And it has been used to emphasize that the Gini index is an intermediate measure between the entropy and the classification error. In practice, misclassification error does not perform well. Classification error does not perform well. So we generally prefer using either the Gini index or the impurity, sorry, or the entropy, right? So in practice, classification error does not perform well. So we generally prefer using either the Gini index or entropy over it. So this is your Gini index. It's a degree of randomly chosen data points being being classified incorrectly. The formula of Gini index we already have seen. It indicates Gini index of 0 indicates, if it is 0, it indicates that all the data points belong to a single class. And my Gini index, if it is 0.5, it indicates that data points are equally distributed among the different class. Equally distributed among the different. So suppose you have a data set with 2 class labels, and if the data set is completely homogeneous, that is all the data points belong to label number 1, then the probability of finding A data point corresponding to label 2 will be 0, and that of label 1 will be probability of 1. So probability of 1 will be P1 will be 1, P2 will be 0, and Gini index will be exactly equals to 0 if it is correctly classified, and will be lowest in such cases. And hence, the higher the homogeneity, lower the Gini index. So it's a relation that higher the homogeneity, lower will be the Gini index. Right? As you can see in this figure as well. Here homogeneity is completely 1, right? 100%. Here it is 50%. So higher the homogeneity, lower will be your Gini index. Higher the homogeneity, lower the Gini index. Now entropy. What is entropy? It quantifies the degree of disorder in the given data set. Its value varies from 0 to 1. Entropy and the Gini index are similar numerically. Entropy and Gini index are similar numerically. Right? Entropy scaled and Gini index are similar numerically. If a dataset is completely homogeneous, then the entropy of the dataset will be 0 and there is no disorder in the data. If the entropy is 0, there is, I can say, there is no disorder in the data. If a dataset contains an equal distribution of both the classes, that is entropy of the dataset will be 1. If the entropy is 1, then it's disorder, complete disorder in the data. Hence, like Gini index, higher the homogeneity, higher the homogeneity, what will be the case? The lower will be the entropy. Higher the homogeneity, lower will be the entropy. Are you guys getting this fact now, everyone? Is it clear? See here, the entropy is 0. Then there's no any disorder in the data. Means 100% homogeneous. If the entropy is 1, 50%. So I can say that higher the homogeneity, lower will be the entropy, right? And now that you have understood the different methods to quantify purity and impurity of a node, how do you identify that the attribute result in the best split or not? How do you identify that? We'll see this. So there's one important concept of um change in the impurity, that is information gain. We call it as information gain. That is coming into the picture now, and which is very, very important part. Like you have understood the concept of uh, you have understood the concept of purity and impurity of a node, but how do you identify the attribute that results in the best split? How do you identify this? Let's hear more about this by just talking information gain, right? So what is that? Before this, you should understand what are, and it is also beyond the scope of your uh, syllabus, but I'm just adding it that you have CART model, you have C4.5 model. Anyway, this is not important for you guys. C5.0, ID3, and we have CADE or CHADE. First is only widely used, and you guys will be using throughout your course and industry. That is CART, classification and regression trees algorithm. But we still have C4.5, C.50, ID3, and CHADE. These are some algorithms that is also we use for decision trees, right? Now, just consider the scenario where you have a split as age is greater than 40, whether it is yes or no here, and you have binary decision tree. This is known as binary decision tree. We have only two subset, right? Yes or no. What about another thing? Let's say you have another which is pain type. Pain type. We have 1, 2, 3, 4. 1, 2, 3, 4. So this is known as multi-way decision tree. Multi-way decision tree. Right? This is known as multi-way decision tree. Okay. So your criteria for splitting is, suppose you have a data set over here. Let's take this. Okay. You have a data set over here, and in that, let's take this two color. 1, 2, 3. Then you have 1, 2, 3. Then you have 1, 2, 3, right? I think 1, 2, 3, 4. Okay. Let's take one more. 1, 2, 3. Right? So this is known as purity before split. And then we select split condition that maximize this gain of purity. We select split condition that maximizes the gain of purity. Then after that, after splitting, let's say we have these two splits, 1 and 2, this one. Here, let's say we have 1, 2, 3, 4, 5, and we have these two classes, 1, 2, 3. Another is, let's say we have 1, 2, 3, 4, 5, 6, and here we have this 1, 2, 3, 4. So this is your purity after split. This is your purity after split, right? And again, you do splitting, and the condition of the best split is impurity post split should be less than impurity pre split, right? That is, split that does this best is chosen as the best split. Split that does this best is chosen as the best split, right? So that is your condition. Can Gini index greater than 5? 0.5. It cannot be greater than 0.5, no? See, beyond this, do you have any misclassification? 50-50 is the maximum possible misclassification, yes or no? Let's say if it is 60-40, then it will be less than 0.5. right? So it is always in the range of 0 to 0.5. That's all. It's always in the range of 0 to 0.5 because that's the formula. From formula, you can calculate. You can take different examples, different scenario, and you can calculate that. No issues. Now, what we are talking about is we are talking about this concept that this is my purity before split. This is my purity after split. And my criteria is impurity post split should be less than impurity pre split, right? Our main agenda is to gain the pure nodes, right? Or why we are doing decision trees is we have to minimize the impurity. We have to maximize the homogeneity. So the criteria for the best split should be split impurity, what we can say, impurity post split should be greater than impurity, should be less than impurity pre split, right? So impurity should be less. After splitting, impurity should be less. So what I'm doing now is I'm removing this thing, everything which we have discussed, and I'll just paste it over here. Yeah. So this is something which will not require this one. Okay. So that is what information gain. That is why we are interested to study the information gain, right? Now, the change in the impurity or the purity gain is given by the difference of impurity post-split from the impurity pre-split. So that is the change in the impurity equals to impurity pre-split minus impurity post-split. And the post-split impurity is calculated by finding the weighted average of the two child nodes. That is not something which you should discuss. The split that result in a maximum gain. Suppose if you are doing this split and the gain, that is change in the impurity, is 0.8, let's say. Here change in the impurity is 0.3. So which split should you select? We should select the split that results in maximum gain as the best split. Yes or no? To summarize this, this decrease in the entropy is known as information gain. That is nothing but we calculate the information gain, we calculate the change in the entropy, and change in the entropy should be as high as possible so that that particular point is selected as the best split, right? So that's what your information gain is. That's what your information gain is, right? Now, let us understand this by taking an example over here, real-time example, right? Okay. So here we have concept of entropy. Suppose I have this decision tree where the main is 8, 4. I've splitted this based on the feature 2, 5 yes, 2 no. Based on the split 3, 3 yes, 2 no. And I'm calculating the entropy, which we have seen the formula. For feature number 1, I'm getting, feature number 2, I'm getting 0.85 as the entropy. Feature number 3, I'm getting 0.966 as the entropy. And always remember that higher the entropy, lower will be the purity and higher will be the impurity. So we should select that particular split where we have the less entropy. But what about the information gain? So suppose you have this example. Let's say You have a data set where you have to predict whether the person will go to gym or not. Let's say it's 2025, right? And everyone is excited. They have set their resolution that I should go gym at least 1 month in this particular year, right? And everybody knows what happens to the resolution. So your two features are, suppose you have a data set where you have features as energy and feature as motivation, and here person will go to gym or not, right? Now I have two features, that is energy, which takes two values, high and low. I have two second, that is motivation, which takes three values, that is no motivation, neutral motivation, and highly motivated. Now what I'm doing is I am interested to select this thing. Yeah, this one. So my feature one is energy, whether energy is high, energy is low. If my energy is high, I'll just highlight this. So based on which feature we should do splitting? That is our question is. So I have energy and I have motivation. So let's go with energy first, right? Now you have been given in the data set itself that if if you select the feature energy, 16 people will go to gym, 14 people will not go to gym. If energy is high, if energy is high, 12 people will go to gym, 1 people will not go to gym. If energy is low, only 4 people will go to gym and 13 people will not go to gym. What have you done is now you have taken the change in the information, change in the entropy, that is information gain. So you have done this calculation of entropy, given the condition, everything is done, and your information gain is 0.337, that is change in the impurity or change in the entropy, right? It is 0.37. Second case is your this one, motivation, right? This time motivation. Now 16, 14, same data set you have. Out of that, you have no motivation, neutral motivation, and highly motivated. If there is no motivation, 7% will go to gym and 1% will not go to gym. If there is neutral motivation, only 4 people will go to gym, 6 people will not go to gym. If there is if there is high motivation, highly motivated, only 5 people will go to gym and 7 people will not go to gym, right? And out of this, you are doing again the same thing, conditional entropy, and information gain. So change in the entropy, if you select this motivation as the node to split your decision tree, the information gain is 0.13 now, right? This calculation is not needed for you because nobody will ask you to calculate that. But we are understanding the significance of information gain. Here it is 0.13 and here it is 0.37, right? If I select energy as a split, I'm getting 0.36 as the information gain. If I select motivation, it was 0.13, right? 0.13. Yeah, 37. So which feature we should select to go for the splitting, right? I have explained this over here. Now it's your time to answer this question. We should select which feature. Either we should go with energy or we should go with motivation. What do you feel?
Motivation, we need to select.
Why motivation you should select?
Yeah, you say always we need to take the lesser one.
Where you have read that lesser one? What I have said over here, what I have explained, change in the impurity should be the split that results in maximum gain, that is maximum change in the impurity, is the best split, right? It's the best split. So
Okay,
the gain should be as high as possible, not as low as possible.
okay. As high as possible means energy only.
right? You can consider, you can relate this to this example. Let's say you guys are interested for your weight loss journey, right? You want, suppose there are two guys, one and two, both are 100 kgs, both are 100 kg. First guy and second guy, they have started their journey, let's say from 1st Jan itself, and by the end of this, let's say year, by the end of this year, this guy has reduced 30 kg, right? This guy has reduced 30 kg. And what about this? This guy has only able to reduce, let's say 20 kg. So reduction, that is information gain, is 20 kg for this guy. For this guy, information gain is 30 kg. Yes or no? So which one is good now? 30 is good or 20 is good?
Yeah, 30 is good.
Right? So that is what your decrease in the entropy is, no? That is what your information gain is. So when there is a change in the entropy, when there is a decrease in the entropy, it should be as maximum as possible. But when you are considering only entropy, it is not the change in the entropy. What is this? This is only the entropy. What do you mean by entropy? It's a impurity. So always remember, higher the entropy, in this case, let's take, there are two guys, one is 100 kg, another one is, let's say, 85 kg. Let's say these are the entropy values for you. And which one is good now? Is it 100 or is it 85? Which one is fit? Which one is healthy? Who is healthy? 100 guy or 85 guy? 85. So that is your entropy. Entropy should be as minimum as possible. Your weight should be as minimum as possible. Your weight should be minimum. But the decrease in the entropy, that is information gain, that is decrease in the weight. Here it is 100 to, let's say, 70, 30 kg. And here it is only 85 to 75. So which one is good now? 15 or 30? Which transformation is good? 15 or 10? Obviously this 30. 30, right? So information gain is the change in the weight you can consider, and entropy is just a weight, right? Is it clear now, this part? Information gain. Is this thing clear to you? So the
Yes,
information
sir.
after splitting the original data set, it should be as maximum as possible. And in entropy should be as minimum as possible. Simple. There should not be any confusion. Now that is what we have. I can take one more example to understand, to explain this particular fact by taking the same example of cholesterol and something like your age. And by doing that, we'll do this thing. But before that, let us have a 5 minutes or let's say 7 minutes break. If you have any questions, you can ask. Otherwise, we'll just go to next part. That is the comprehension of Gini index. We'll take the same example that we had, the doctor example, right? It's a lot of mathematics. Let's have some break. Let's fresh it up little bit and then do again the challenging mathematics part, right? All right. So we still have left with the hyperparameter tuning that we can do it by the end of this session. Okay. Okay, we can have it straight up to 12 o'clock then. Let's try to stretch this up to 12, 3 hours a session, right? Let's do this. Let's have a break first before that. Let's have a significant amount of break. Let's say 10 minutes. Let's take break till 11:20. Yeah. Okay, all right. Let's see this. Now let us consider the hard disease example that was introduced uh, in the earlier segment to understand decision trees. Now you will calculate the homogeneity measures for some of the features on some numbers using the Gini index to determine the attribute that you should split on first. So the data set is not homogeneous, which is given to you, and you need to split the data in such that uh, you need to split the data such that the resulting partition are as homogeneous as possible. And this is a classification problem, right? So there are two output class labels. There are two output class labels. One is having heart disease or not, and hence you use the Gini index as the homogeneity measure. You are going to use Gini index and calculate the homogeneity. Let's go ahead and see how the Gini index can be used to decide where to make split on the data points. And while making your first split, you need to choose an attribute such that the purity gain is maximum, right? That is information gain is maximum. You can calculate the Gini index for the split on sex and compare that with the Gini index of the split on cholesterol. So we have two features, sex and cholesterol over here. Suppose you give the data for 100 patient and the target variable consists of two classes, that is class 0, which is having disease, and okay, let's put it like this, no disease and disease, that is 40 plus 1. Now expressing this in terms of probabilities, you get probability of 0 equals to 60 divided by 60 plus 40, that is 0.6, right? And probability of 1 would be 40 divided by 60 plus 40, that will be 0.4, right? Now you calculate the Gini index for the data before making any splits, which is as follow. Gini impurity formula, which we have seen. I'll just do this. Don't worry about the formula. Don't worry about the calculation. P11 minus P1. And it will be 0.6 into 1 minus 0.6 plus 0.4 into 1 minus 0.4. It will be 0.48. 0.48, right? Now let us now evaluate which split gives the maximum reduction in impurity among the possible choices. What is our target? Yes, information gain or gain after splitting, gain of impurity after splitting will be as maximum as possible. So you have the following information about the target variable and the two attributes. You have classes, you have no disease, you have disease, you have total, and you have sex column, and you have total column, right? So sex, in that we have male and female. You have no disease 50, this is 10, no, this is 10, this is 20, 20. Total would be 50 plus 20, 70, 10 plus 20, 30, and horizontal total will be 50 plus 10 is 60, 20 plus 20 is 40, total will be 100, right? That is your data set, which is given to you. Right? Now, again, we have cholesterol level. So this is your features slash classes. Here also, this is your features slash classes. We have no disease and we have disease. Okay, let's make it classes over here. We have disease, we have no disease. We have features over here slash classes. Just a moment. Features over here, classes over here, and we have features over here, right? Now, based on the cholesterol level, it is less than 250, it is greater than 250. Here it is total, right? And no disease. And disease. Let's say you have 50, no disease. If you do split based on the cholesterol less than 250, no diseases are 50, diseases are 10. Greater than 250 is 10 and 30. This is just a hypothetical example that we are taking, right? And here is your total. So 50 plus 10 is 60, 10 plus 30 is 40. Here it will be 60, here it will be 40, and it will be 100. So now if I just do this, I do this, if I do this, this one. So now we have these two conditions, and as you can see in the table, it shows that number of diseased and non-diseased person with respect to the levels of two attributes, sex and cholesterol. With respect to two attributes, sex and cholesterol. Split based on the sex, we'll just consider. Let's consider first candidate split based on the sex or gender. As you can see from the first table of the 100 people, you have 70 males and 30 females. Among the 70 males, that is child node, among the 70 males, uh, among the 70 males, child node containing males, 50 belong to class 0, that is no disease, 20 belongs to class 1, right? Class 0 is your no disease, class 1 is your disease, right? So let's do that. Let's write down over here. I'll write down split based on sex. We have 70, 30, right? Here we have 70, here we have 30. And out of them, here male, here female. Class 0, class 1 are 50, 20, right? 50, 20. Female is 10, 20. 10, 20. So I'm just taking this figure and I'm doing it over here. This one. Okay. Now the probability of the two classes within the male subset counts out to be 50 divided by 70, 20 divided by 70. So let's say probability of class 0 will be 50 divided by 70. And probability of class 1 would be 20 divided by 70. 20 divided by 70. Right? Now the probability of the two classes, using the same formula, this time Gini impurity becomes 50 divided by 70 becomes 0.714. 20 by 7 becomes 0.286. Now Gini impurity will find 0.714 into 1 minus 0.714. That is probability of 0 into 1 minus probability of 0, right? Plus probability of 1 into 1 minus probability of 1. That's your formula. And that becomes 0.714 into this 1 minus 0.714 plus 0.286 into 1 minus 0.286. That becomes your 0.41. That becomes 0.4. Now let's now take another case, that is child node containing females, where there are 30 females, out of which 10 belongs to class 0 and 20 belongs to class 1, right? Again, we'll find probability for male. This is male, this is female. Let's take the same case over here. That is this. It will be 10 and 20, right? 10 this side, 20 this side. Now what you'll do is you'll again find the probabilities of 0 class. That is your 10 by 30. Probability of 1 will be 20 by 30, right? Now using the formula, Gini impurity for female becomes, this becomes 0.333 This becomes 0.667. Now, do you the entropy or the information gain will be, as this is 0.41, here it will become 0.3. Right? You try to calculate this. I already have done that. 0.3 is the answer. Now, how do you get overall impurity for the attribute sex after a split? You can aggregate the Gini impurity of these two nodes, that is 0.41 and 0.3, by taking weighted average of the impurity of the male and female nodes, which will become, this time probability of male will be 70 by 100, that is this 70 by 100, which becomes 0.7, and my probability of female becomes 30 by 100, and that becomes 0.3, right? Now this gives the Gini impurity after the split based on the gender as male 0.7 into Gini impurity of male is 0.41, so I'll write down 0.41 plus female probability is 0.3, and uh, sorry, Gini impurity for female is 0.44. I just have calculated this. It will be 0.333 into 1 minus 0.333 plus 0.667 into 1 minus 0.667. That becomes your 0.44. Sorry. So this is probability of female into Gini impurity of female will be 0.44. So I'll write down that 0.44. And if you just take this, I'll just copy this and I'll just put it over here. It becomes correct use of bracket, and this should be 0.41. It becomes 0.419, right? So Gini impurity before split, is 0.48, right? We have calculated that. Gini impurity after doing splitting based on the sex column is Gini impurity after the split based on age is 0.419, right? Here it will be 0.48. This is before split. Let me write down over here. This is before split, right? Now it's time to find the reduction in the impurity. Reduction in the impurity. What is that? It will be 0.48 minus 0.419, which is exactly equals to this. 0.48 minus 0.419 minus, which becomes 0.06, right? And here you get the following tree after splitting. That is my entropy reduction. That is my information gain is 0.06. Now, same thing we can do it for cholesterol, right? Same thing we can do for cholesterol. I'll just quickly write down over here. This is based on cholesterol. Cholesterol, right? It is 60, 40. You can see over here. We have 60, 40, right? Now I'll do the splitting, which is over here. This is less than 250. This is greater than 250, right? And here you'll have different values. Here you have different values. And here it is 50, 10. Here it is 10, 30. Right? Now, uh, I can take this out and let us do this split calculation, impurity gain and that calculation, which we have done for the sex column. We can do it for cholesterol, right? So to just write down over here, this is your reduction in the impurity, which is 0.061. And let us try to find it for cholesterol, right? Now the probability of class 0, uh, for this class cholesterol, it is 50/60, and class 1 is 10/60 for less than 250. So I'll write down over here. It will be 50/60, and probability of class 1 will be your 10/60, right? This is 0.833. This becomes 0.167. 0.167. Now, using the formula, gene impurity for low cholesterol subset, which is 0.833, 1 minus 0.833 plus 0.167 into 1 minus 0.167, which is exactly equals to 0.27. Right? Now, let's take the other case over here, greater than 250. Probability of class 0 will be 10/40, class 0 will be 30/40. Let's do that. This is my less than 250, right? This is my greater than 250. So probability of 0 for this case will be 10/40. Probability of 1 will be 30/40. And as you know, 10/40 is 1/4, 0.25. This is 3/4, this is 0.75, right? Now let's do the calculation. 0.25 into 1 minus 0.25, right? Plus 0.75 into 1 minus 0.75, which is 0.37. The overall impurity for the data after the split based on the cholesterol can be computed by taking the weighted average of the impurities of the high and low cholesterol nodes. So probability of low cholesterol node is 60/100, that is 0.6. High cholesterol node is 40/100, right? So I'll just write down over here probability of low cholesterol will be 60/100. Probability of high cholesterol will be 40/100, right? And this gives the Gini impurity after the split based on the Gini impurity after the split based on cholesterol, which will be 0.6 into 0.27, right? Above this one. 0.27 plus this is 0.37 and this is 0.4. So probability of high cholesterol into impurity, Gini impurity of the low cholesterol, that is 0.37, right? That we have done over here. This we have used these two values, and we have used this value, and we have used this value, this one. Perfect. Now, thus the split based on cholesterol, based on cholesterol. Before we had 0.48, yes or no? Before we had 0.48, this one. Before we had 0.48, now it is, let's calculate this, equals to this, 0.31, right? After splitting based on the cholesterol, it is 0.31, and the reduction, the information gain is equals to this minus this, simple, equals to this minus this, 0.17, right? So my reduction after doing cholesterol is 0.17. My reduction in the impurity after doing split based on the age is 0.61. Now, which is the best split? What do you feel? Which one is the best? Yes, guys. Cholesterol. Very good. So thus the split based on the cholesterol gives me the highest amount of information gain, that is decrease in the impurity. Hence, from the above example, it is evident that we get a it is evident that we get a significantly higher reduction in Gini impurity when you split the dataset on cholesterol as compared to when you split on gender, right? Let us summarize this all steps that you have performed. Anyway, you can do this thing. So what I'll do is this process of calculating this thing, I think it's clear for you. Let us not waste our time in summarizing the steps that we have performed till now. Let's go to next part. That is, let's go to next part. That is impurity measures, sorry, feature importance in decision tree. That will be perhaps last part of today's session. Feature importance of decision trees. Feature importance of decision trees. Now, it's again very, very important thing that uh, that is the advantage of decision tree, right, over linear model. I have written this point at the time of defining the advantages of decision trees, tree-based model over the linear regression model, which we have discussed in the first half of the session. That is tree-based model over linear model. What are the advantage? This is first, this is second, this is third, and this is fourth. That is decision tree often gives us an idea about the relative importance of the explanatory variable. How does it gives? That is something which we have seen just now. So if the if I select age and if I do the splitting, my information gain is only 0.06. That is the reduction in the entropy, right? If I take cholesterol, my reduction in the gain, that is information gain, reduction in the impurity was quite high. It was 0.17. The reduction in the entropy. Now, which one is the good? Which one is the uh, important feature according to this two? Important feature is cholesterol. Yes or no? Because if I do splitting based on my cholesterol level, my feature importance, my reduction in the entropy is 0.17. It is high. So cholesterol is the high important feature as compared to age in our data. So I can say feature which gives, right? Feature which gives maximum reduction in impurity, maximum reduction in the impurity is the most important feature. Yes or no? So that's the reason we calculate the information gain to understand which feature is important for us, right? That is another use case scenario. So cholesterol is more important feature as compared to gender. Cholesterol is more important feature as compared to gender. That is what we have. I think we can stop here for the day. Let me check what is left for us. Okay. So decision tree will summarize this. It helps in quantifying the importance of each feature by calculating the reduction in the impurity for each feature at a node. And this feature that results in a significant reduction in the impurity is the important variable. And the one which results in the less reduction in the impurity is the less important feature, less important variable. And in the previous example, the cholesterol variable resulted in higher reduction in the impurity as compared to gender. This implies that cholesterol will help distinguish between the two classes better than gender. This is intuitive as well because, as you can see, if you see real case scenario, splitting on cholesterol is expected to be more important, right? If you are just consider you are being a doctor, and it is more important and informative for you to check, to further have a check of your heart disease. Yes or no? Is it my gender variable is important? Is it related to heart disease? This is because medically people with high cholesterol have higher chances of developing heart disease than the ones with low cholesterol. Simple, right? So that's what we have. I think let's um, do you want to let me just check. Um, anyway, this calculation of information gain is not needed. We not discuss that. Okay, let us discuss the next session agenda. In tomorrow's session, we are going to start with the practical implementation. So it will not be boring as compared to today's session. We are going to see the hyperparameter tuning in decision trees, right? So in the previous session, you learned about the concept of homogeneity and its various measures. In this session, you will first understand the disadvantages of decision trees. Disadvantages. Disadvantages of decision tree. Then you will learn about various truncation and pruning strategies that are used to overcome one of the biggest advantages of decision trees, truncation and tree pruning. Very, very important part. And then we'll see hyperparameter tuning, and then we'll see decision tree regression. So that will be your agenda for the tomorrow session. Let us discuss disadvantage of decision tree first. Let us discuss disadvantages of decision tree first, and then we can stop here for the day, right? Okay. So disadvantages of decision tree. As we already have discussed this, um, it is overfitting model. What do you mean by overfitting, guys? What is overfitting?
When the model learns the pattern and it performs well on training data, but when it's given unknown data, it does not perform well.
Very good, very good. So it's very important concept. You should know the overfitting concept. You will find this question n number of times in the interviews, and you should be able to defend that particular question. You should be ready with your overfitting questions with everything, every weapon that you have. What is overfitting? How do you overcome overfitting? How do you test that? How do you remove overfitting? Right? You should be ready with this question. You should be ready with all the weapons that you have for this question, right? So, what is overfitting? How model gets overfitting? How is overfitting? Why model gets overfit? How do you remove that? How do you treat, or what are the different ways to remove the overfitting? right? Very, very important question. Okay, so disadvantage of decision tree is, first of all, it is overfitting. It is always an overfitting model. That is a curse given to this model. So it's a overfitting, and um, so what happens is, after splitting, as I discussed, it is a greedy model, right? Greedy. So it's an unstable model. Like, you do not have any control on how the further splitting happens, right? It does not things beyond the first step itself. Like, if I do splitting based on the age, let's say, and if I just put a criteria, age less than greater than 54, age less than 54, I don't the model is not able to visualize what will happen in the next segment itself, right? So it's a greedy, it's unstable, right? First is, it tends to overfit the data, and if allowed to grow, if allowed to grow, if allowed to grow with no check on its complexity, no check on its complexity, a decision tree, a decision tree will keep splitting until it has correctly classified all the data points, all the data points in the training set. Second is unstable. Second is unstable. What do you mean by unstable? They tend to be quite unstable, which is implication of overfitting only. A few changes in the data, few changes in the data can considerably change a tree that you have. So that is what your problem is, right? Now I'll just put a question that uh, I'll just put one question. You have to find which is the most overfitting, which is the most informative feature for this particular tree that you have. So we have one variable thl, let's say it's hal. I don't know what is that, but we have this question, right? We have yes, we have no. Yes is pane type. Yes is pane type less than 3.5. And this is no may, you have fluorescent. Again, don't give focus to this column. What is this column is all about? And after this, you have only one. After this, you have fluorescent same less than 0.5, less than 0.5. This is one. This is one. This is two, right? And here, after fluorescent, this is two data set. Then you have exercise column less than 0.5. You have age now greater than or equals to 51. This is one, this is two, and this is two. Here also this is two. So basically your decision tree is like this, and you have to find which is the most informative feature as identified by a tree. Just let me just give me 1 minute, not 1 minute, 10 seconds. I'll just take out that figure for you so that you guys will be easily visualize that, right? Because my drawing is very poor. Okay, so this question which I have taken is related to okay, so it's that. Okay, this is your question. Let me share my screen. Yeah, this is your question for So you have to find which is the most informative feature as identified by the tree. Right? Which is the most informative feature. Again, I understand this is not at this point of time you will not be able to uh, get this, but features which are chosen that they maximize the homogeneity of this after the splitting, the tree will pick those features first that maximally increase the homogeneity in a way of providing maximum information about the day, about the data. So the most informative feature that you have will always be features are always towards the top of a tree. Why? Because as you have seen from this example, you have to split. Splitting should be done based on the cholesterol, not on the age, because your cholesterol has the maximum reduction in the entropy, that is impurity, which is 0.17, and that is why your cholesterol is the most important feature here, right? In this case, in this example that we have, this thal 4,5 is considered is taken as the first splitting because of the fact that if you do splitting based on this thal less than 45 4.5, you are able to achieve maximum information gain, right? You are able to achieve the maximum information. That is why it is kept at the top over there. That is why it is kept at the top. Right? Now is it clear, guys? Why it is at it is kept at the top? Because the most informative features are towards the top of a tree, right? चलो, ठीक है. That is what we have. You just go through this all the things which you um, can have. You can revise. I already have written this over here. You can revise this on the sheet itself, and then we'll stop here for the day. Okay. All right then. We'll stop here for the day. If you have any questions, you can ask. Otherwise, we'll just stop here. Yes, guys. Anybody have any doubts, any questions? Yes, guys. Do you have any questions, any doubts, anything to discuss? All right, then if you have any, if you don't have any questions, we'll stop here for the day. In tomorrow's session, we are going to see some hands-on in Python, right? So don't worry, it will not be as boring as this session was, which was pure theoretical one. In tomorrow's session, we are going to do some hands-on part as well, right? चलो ठीक है, then we'll stop here for the day. Thank you. Happy learning. Bye.